Hello friends, welcome back to Science Education to learn one more new tutorial. In this tutorial, we are going to learn about pressure measurement devices. So friends, pressure measurement is very important thing in industries like measuring steam pressure coming from boiler or in oil and gas fields. It is important so as to avoid any leakages and explosions. Also, it is not only required in industries but in our day-to-day life as well. Like we need to closely monitor the pressure in our car tire or gas filled in our car as a fuel. So let's get started with the today's tutorial and let us see what are the topics we are going to learn today. So the first one is what is pressure and its units. In brief, we are only going to learn this topic in brief, but if you want to learn this topic in detail, then you can go through my other video tutorial uploaded here, which is mainly created for what is static pressure in detail. Then we are going to see the second topic, that is pressure measurement, and we are going to see few terms related to pressure measurement. Then comes pressure transducers, and the last we are going to see few pressure measurement devices in detail about how they work, what is working principle behind. So what is pressure? In simple words, it is the force acting per unit area. It says that it is the amount of force which acts on unit area. And what are the units of pressure measurement? So the standard unit for pressure is Pascal, which is Newton per meter square. There are few more units of pressure used commonly, which is bar and PSI, which means pound per square inch. So friends, before moving to the actual pressure measurement devices, let us first understand few topics. So the first one is pressure measurement is basically divided into two types, that is static and dynamic. When pressure source is constant, that is air pressure in our car tire or a balloon filled with air, this type falls under static pressure. But when we are measuring fluid pressure in which fluid is not static but it is moving, then it is called as dynamic. Measuring pressure of gas pipeline or water pipeline are the examples of dynamic pressure measurement. Next term to understand is that all pressure measured is a relative term, depending upon which measured pressure is divided into three types, that is absolute pressure, gauge pressure and differential pressure. So when pressure is measured relative to the zero or a perfect vacuum, it is known as absolute pressure. When we measure a pressure relative to the atmospheric pressure, it is called as gauge pressure. And when we measure the pressure difference between 2 points, then it is called as differential pressure. Pressure transducer. It is a device that converts one form of energy into other form. So we can use this device for pressure measurement. Since it converts one form of energy into other, we can use this to convert pressure energy into mechanical or electrical signals, and these signals can be measured. So depending upon the output signal, these transducers are divided into two types. First one is mechanical and second is electrical. Few examples of mechanical transducers are Burden tube or bellows, and in electrical transducers pressure energy is converted into electrical signals, and few examples of electrical transducers are strain gauge, capacitance gauge, or piezoelectric gauge. So let's see how burden tube gauge works. So burden tube is basically a mechanical pressure measuring instrument, and thus it operates without any electrical power. Burden tubes are radially formed tubes with an oval cross section. The pressure of the measuring medium acts on the inside of the tube and produces a motion in the non-clamped end of the tube. This motion is the measure of pressure, and it is indicated via the movement of needle. Next device is manometer or U-tube manometer. So in manometer, it is the device in which column of suitable liquid are used to measure the difference in pressure between 2 points or between a certain point and the atmosphere. One end of manometer is connected to a pipe or a container having a fluid whose pressure is to be measured, while the other end is open to the atmosphere. The lower part of U-tube contains a liquid which is immiscible with the fluid of which we are measuring the pressure, and it is of greater density than that of the liquid. This fluid is called as manometric fluid. Manometer basically works on hydrostatic law, that is, hydrostatic pressure exerted by a liquid column. In manometer, unknown pressure is determined by balancing it against some known pressure or vacuum. Now let us see few of the electrical pressure transducer. So the strain gauge. If a metal piece is subjected to a tensile stress, the metal length will increase, and thus will increase the electrical resistance of the material. This principle is used in pressure measuring devices. The devices are designed in such a way that on one side of elastic membrane, these thin wires of strain gauge are attached, and from on the other side, unknown pressure which we are going to measure is allowed to act. Due to this unknown pressure, elastic membrane gets deflected and gets stretched. The strain gauge, which eventually changes the resistance of strain gauge. So when elastic membrane gets stretched, it eventually stretches the strain gauge or thin wires which are attached on the other side of elastic membrane. And due to this stretching or strain in wires, the resistance of the strain gauge gets changed, and this resistance is proportional to the pressure acting on the elastic membrane. So in this way we can measure the pressure using strain gauge. Next one is capacitance transducer. The capacitance transducer is nothing but the capacitor with variable capacitance. The capacitive transducer comprises of two parallel metal plates that are separated by the material like air, and when the distance changes, the capacitance also changes. Now this gauge is designed in such a way that when unknown pressure is applied, the distance between two plates varies, and eventually the capacitance as well. And by measuring these changes in capacitance, we can measure the pressure. Now the last type of electrical transducer, that is piezoelectric transducer. Piezoelectric device takes advantage of electrical properties of crystals such as quartz. These crystals generate an electrical charge when they are strained. So these crystals are arranged in one conducting element, and when pressure to be measured is allowed to strain this conducting element, some charge gets generated in conducting element, and this charge which is generated is proportional to the strain which is occurred due to the applied pressure. So in this way we can measure the pressure using piezoelectric devices. So friends, this was all about the pressure measurement, and I hope you have understood the topic well. So don't forget to subscribe my channel for more such tutorials. And if you are having any doubts, please comment below. Thank you for watching.
Burden tube pressure gauge. Burden tube pressure gauges are used for the pressure measurement of relative pressure from 0.6 bar to 7,000 bars. They are classified as mechanical pressure measuring instruments and thus operate without any electric power. This video will cover the followings. 1. Working principle of burden tube pressure gauge. 2. Construction. 3. Working. 4. Advantages and disadvantages. If you are new to ADTW, click on the subscribe button below and turn on the notification to get all the updates from our channel. Working principle of burden tube pressure gauge. When an elastic transducer, such as burden tube in this case, is subjected to a pressure, it deflects. This deflection is proportional to the applied pressure when calibrated. Construction. A C-type burden tube consists of a long thin-walled cylinder of non-circular cross-section which is sealed at one end. This tube is made from materials such as phosphor bronze, steel, and beryllium copper, and attached by a light mechanism which operates the pointer. The other end of the tube is fixed and is open for the application of the pressure which is to be measured. The tube is soldered or welded to a socket at the base through which the fluid, whose pressure is to be measured, enters the C-type burden tube. Working of burden tube pressure gauge. As the fluid under pressure enters the burden tube, it tries to change the cross-section of the tube from oval to circular, and this tends to straighten out the tube. The tip of the burden tube is connected to a segmental lever through an adjustable link. The segmental lever end on the segment side is provided with a rack which meshes to a suitable pinion mounted on a spindle. The segmental lever is suitably pivoted and the spindle holds the pointer. The resulting movement of the free end of the tube causes the pointer to move over the scale. In real-life application, the pressure gauges are mounted with siphon tube. Siphon tube is a simple device used to protect a pressure sensor from high-temperature media, such as steam. It can also be used to reduce the potentially damaging effects of rapid pressure changes. When first installed, the siphon should be filled with water or some other suitable separating medium. This medium continuously remains in contact with the burden tube. Burden tubes are generally made in three shapes: C-type, helical type, and spiral type. Advantages of burden tube pressure gauges. 1. These burden tube pressure gauges give accurate results. 2. The cost of burden tube pressure gauges is low. 3. Burden tube are simple in construction. 4. They can be modified to give electrical outputs. 5. They are safe even for high pressure measurement. 6. Accuracy is high, especially at high pressures. Disadvantages of burden tube pressure gauges. 1. They respond slowly to changes in pressure. 2. They are subjected to hysteresis. 3. They are sensitive to shocks and vibrations. 4. Amplification is a must, as the displacement of the free end of the burden tube is low. 5. It cannot be used for precision measurement. If you want more in-depth videos like this, then subscribe this channel and click on the bell icon to get notified for every special video we upload. Also, if you have any doubt or opinion, comment it below. And help us by sharing this video with your friends.
Hello, this is Peter Wielander, Process Industries Editor for Control Engineering. Welcome to the second of our basement videos. You can see we've moved upstairs today because we need something with a little more ceiling height in the basement, because we're going to talk about measuring the level of liquid in tanks. Now, if you can hear me over my neighbor's leaf blower, it is November after all, we're going to look at this, and we have as our main object of the lesson today a 6-foot tall tank. Well, it's a tank that's actually a piece of 6-inch Schedule 40 PVC pipe, but we've outfitted it with a cap at the bottom and a nice section of clear tubing that will function as a sight glass, so you'll be able to see how much water's in it. There's nothing in there right now, but we're going to be filling it in just a second.
The concept is really very simple. Liquids have weight, and we can measure that weight in the form of pressure. If we insert a pressure gauge near the bottom of the tank, the weight of the liquid above the gauge will register according to its depth. The more liquid above the gauge, the higher the pressure reading. If we know the density of the liquid, the pressure reading can be converted to depth. For our demonstration, we have tapped a hole near the bottom of the tank and connected a tube, or impulse line, to a Rosemount 3051 pressure sensor. The device is configured to measure pressure in inches of water column, but any unit of pressure could be converted to the desired depth reading.
Okay, now let's put some water in here, and you watch and see what's coming through on the pressure sensor. We can see the water coming through on the sight glass. Okay, I think that's enough for the moment. Now that we've got the water in the tank, let's see how close we really are to the actual measurement. If I lift the ruler a little bit off the bottom to compensate for the thickness of the bottom of the cap, I would say that the reading, according to the sight glass, is just about 44 inches. As you can see right now, the pressure sensor actual element is down here, roughly equal with the bottom of the tank. But let's lift it up and set it up here. Pressure reading changes by about 14 inches. Now all this works very nicely if the tank is vented and it's open to the atmosphere and there's nothing else that's going to interfere with the actual static pressure of the weight of the water. But all tanks are not open. So what happens if this tank is sealed? Let's put a cap on top of the tank, as it would be if it were sealed. Let's see if that makes any difference. Okay, now what I've done is I've put the cap on the tank, and I've connected a line to a compressed air tank. Now, bear in mind that a PVC is not suitable for using compressed air. It's just not the right material for that, and neither is clear polyethylene tubing. So we're just going to gas this up just a little bit, just enough to confuse the pressure sensor. Now, watch what the gauge reads. Even though there's nothing happening to the level of the liquid, it's just the pressure inside the tank. We'll just bump it a little bit and see what the pressure gauge says. Now see, with just that little bit of air, the pressure reading changed pretty dramatically. Now it's leaking out. But you can see that had an obvious effect on the reading. If you were using that for the reading, you might say, wow, how come the level changed that abruptly? When in fact it didn't change at all. There is a way to solve that. If you are going to pressurize the tank, and you do still need to use this as your means of measuring level, there is a way around it. Just in the same way that we have the sight glass attached to both ends of the tank, we can attach both ends of the pressure sensor. This pressure sensor, the 3051, happens to be a differential pressure gauge. At the moment, we just have the low side open to atmosphere. But if we connect the low side to the top of the tank and read the pressure of the headspace above it, it will compensate. So now let's pressurize the tank again and see what we see on the differential pressure reading. Now that we're taking a differential pressure reading, where we're reading the weight of the liquid compensated by any pressure inside the tank, we can still get a true reading just as we did when the tank was vented. This is a very simple but very useful method for measuring tank level. It only works with liquids. You probably want to stay away from things where there's going to be sediment, because the sediment might have a tendency to clog the impulse line, or you just have to put the impulse line somewhere above the sediment level and compensate for it. If you're measuring something other than water, if you're measuring something heavier or lighter in density, you can compensate for that as well. You could do it using a mechanical gauge if you wanted, even a mechanical differential pressure gauge if necessary. But if you're going to feed information to a larger control system, or you want to outfit alarms and that sort of thing, an electronic device is going to help you a great deal, because you can send the information remotely, you can trigger alarms for high or low level, any number of things that you can do using this approach. Thanks to the folks from Rosemont for giving us the 3051 pressure sensor. For Control Engineering, this is Peter Wielander. Thanks for watching.
So I have a manometer here, nothing too crazy. I've got an open end tube here, and you can see there's a measuring stick, and I have some fluid filled with water, but originally this was be mercury, because Torricelli's earliest barometer used mercury. In any case, what I'm going to do is I'm going to take a syringe and I'm going to attach it to the enclosed tube, and now I'm going to make the space smaller for the same amount of gas that's trapped in this area. So by me making the space of the volume smaller, okay, the pressure is going to increase. So I am going to, Boyle's law, lower the volume by forcing the gas molecules into a smaller space is going to increase the pressure. The manometer is going to measure that increase in pressure. When the pressure was equal, these levels were equal, because the pressure in the inside of this tube is equal to the pressure pushing down in this open container. So the force on this liquid level is the same as the force on this liquid's level, and thus you have equal pressure. Now by increasing the pressure, and I'm doing this by making the volume smaller, stuffing the same amount of gases in the same temperature and pressure, and making a smaller volume, I'm increasing the pressure. And what we can do is we can measure the difference, okay, of these liquids to measure the pressure. Right now, if I wanted to measure the pressure, if this was mercury, we would say that I'm supporting, if this is 4, and let's pretend this is approximately 23, okay, so this is 19. So from this point here, I'm measuring 19, okay, millimeters. Okay, now of course this I just measured 19 centimeters. So that's 190 millimeters of fluid I'm supporting upward. And I would say that the pressure in this area is higher than the atmospheric pressure pushing down. Right? Manometers use a differential of pressure to measure. So right now, the pressure in this syringe, which is connected, is 190 millimeters of mercury higher than atmospheric pressure, right? There's two forces. There's a force pushing down here and the force pushing down here. Who's winning? Clearly this side is winning by 190 millimeters of mercury, which is, by the way, is a torr. So we would say the pressure in here, if the atmospheric pressure was 760 torr, it'd be 760 plus 190, and that's how we measure the pressure here. Okay, if we go the opposite way, make them equal out again, and now I'm going to lower the pressure by making the volume larger. Whoa, how much higher in pressure is the atmospheric pressure? Well, this pressure is lowered, and this pressure on the open end is winning. Let's pretend it's also 19 centimeters, so let's make that 190 millimeters of mercury. So now the pressure in here is less than atmospheric pressure by 190, and so we would do 760 minus, okay, 190, and that would be the pressure here. So this pressure here is lower. Clearly can see the atmospheric pressure is winning by 190 millimeters of mercury. Okay, and again, the pressure in here is 760 minus. When we did the other side, we did what? We increased the pressure. We did what? We said, well, this is pushing back on the atmosphere, plus it's supporting the column. So this is equal to the pressure outside, but you have to add 190 to it in this case if we're going to use that. Okay, so manometers are used, either subtracting. Here we're equal. Here this side is less than the atmospheric pressure pushing down by this much. And here, the gas here is less than the atmospheric pressure by that much. Now, if we don't have mercury, we can change that into water. So, I'm sorry, if this is water and not mercury, we can compare it to mercury's density by height times density equals height times density. Because if you have mercury, okay, mercury is 13.6 times more dense than water. So therefore, its height is going to be 13 times smaller. A heavier volume of water, okay, cylinder being supported. Remember, we're supporting a certain weight, okay? And that weight, for the same amount of weight of mercury, it's going to be a lot less volume. So if this was water and I'm going to convert it to mercury, okay, I take my, if we're going to use 190 millimeters, I divide it by 13.6, and that would be the height in mercury. So if we don't have water, we can certainly get there by doing those differences. So that's a little basics of manometers.
That's so cool. Can I say hi? Can I be in your video?
You are.
In this video, we're going to use this YouTube manometer to try and measure the gas pressure of the gas in lab 5. So what do we need to do? Well, it's a very simple device. Here we have got a glass-shaped YouTube, not a video hosting site, but a piece of glass shaped in a U shape, and it is filled with liquid which has got a bit water, which has got some food colouring in, so we can see what's going on. And at the moment, the pressure is the same on both sides. Let me just disconnect this so that you can definitely see the pressure. This hose goes just off the top of the screen and into there. The pressure is the same at both ends, just atmospheric pressure. Now I'm going to connect it to the gas tap, turn on the gas tap, and now we can see that the level has increased on this side because inside here, gas from the gas tap has entered here and increased the pressure on this side. And what I'm going to try and do is roughly measure the height difference between the two sides for you. I'm not going to go for super accuracy, but let's pop this meter ruler in there. And it looks to me, looking across, I could do with another ruler, that it's maybe 24 centimetres difference between the two heights.